Okay, geometry, let's get rolling now into section 1.5, which for us is kind of the beginning of the second half of chapter 1. And we've got a section right here that's heavy on vocabulary and diagrams, but there aren't really a whole lot of difficult problems that we have to worry about solving here. So let's take a look as we go through this. Our first vocabulary term, everybody, is adjacent angles. And the word adjacent, that's a D and a J there that are kind of mixed together, sorry. The word adjacent is one of those words that some people feel like they know fairly well and others don't. But if I were to ask you guys a question like name a state that is adjacent to Illinois, a lot of people could come up with an answer. In fact, there are 5 there. Wisconsin, Iowa, Missouri, Kentucky, and Indiana. The word adjacent means next to or touching or sharing a border with. So when we look for a definition of adjacent angles, this is what we're going to write down. Angles with the same vertex that share a common side. Again, that looks like shave a common side, but there we go, that share a common side. So that's the definition, but to be honest, most of us don't do great with these large verbal definitions here, and we would rather see a picture. So to draw that, we're going to draw 2 angles. Well, let me start with 1 angle. So I'm going to put an endpoint right here and draw 1 ray coming out of it, and then a second ray coming out of the exact same endpoint. So there you go, we now have an angle. To make a pair of adjacent angles, and everybody, I should point this out, we're talking about pairs, so there always have to be 2 angles here in order to do whatever it is that we're talking about doing. To draw 2 adjacent angles, I now need to draw a second angle that has the same vertex as the angle that we just drew, and they need to share 1 ray in common. So the easiest thing to do now, guys, is just to draw a third ray coming out of the exact same endpoint, vertex, as the first 2. And now, if I called this point A, and this point here B, and this point over here C, and how about we use a V for the common vertex of all of those angles, we could now say, everybody, that we've got a pair of adjacent angles by looking at angle AVB. That is this angle right here, everybody, and an angle right next to it that has the same vertex and shares a common side. Well, that would be this angle right here, which we will call angle BVC. And that there, everybody, is an example of a pair of adjacent angles. They have the same vertex, that's V. They share a common ray, which is VB. And this is important also, although it doesn't come up very often. They cannot have any interior points in common. Now, don't write this down, everybody, but what if I told you that I thought that angle AVB and angle AVC would be adjacent angles as well? Well, let's think about that. AVB is this same angle here we were talking about a second ago. AVC is this larger outer angle. So as I look at the definition, do they share the same vertex? Yeah, they both have a vertex at V. Do they share a common side? Yes, both of them have ray AV right there. But the reason that these 2 angles are not considered adjacent is because they overlap. This point right over here, let me call that point D, is in the interior of both angle AVB and angle AVC. And you can't have that for adjacent angles. They cannot overlap. So I'm going to get rid of all of this junk that I drew here in green and leave it as it was. AVB and BVC are the only pair of adjacent angles in this figure. So they have to be next to each other, sharing a vertex, sharing 1 common ray, and they cannot overlap. All right, that is adjacent angles. Next one, complementary angles. Now this means a little bit different than the way that complement is intended when it's spelled with an I, everybody. If you give someone a compliment with an I, that's when you say something nice about them. But when we're talking about complement with an E, it means 2 things that work together kind of harmoniously towards maybe a common goal. So our definition here for complementary angles, everybody, are going to be 2 angles whose measures add up to 90 degrees. Okay, nice and simple. Now, very often, complementary angles are adjacent to one another. So probably the easiest way to draw this would be to draw 1 ray over here and then to draw a 90-degree angle. because we're talking about right angles here, and I would need to put a corner mark there to indicate that that angle was 90 degrees. You cannot just assume that an angle that looks like a right angle is a right angle, okay? And then from there, if I drew one more ray coming out of that same vertex and said, okay, here's angle 1 and here's angle 2, well, now as I look at this, angle 1 and angle 2, using the angle addition postulate, would add up then their measures to the measure of the big outer angle, which we know is 90. So we could say that angle 1 and angle 2 are complementary angles, and I'm going to abbreviate that right here. Now this would be an example of complementary angles that are also adjacent angles. They share the same vertex right down here, they share a common ray right there in the middle, and they don't overlap at all. But nowhere in this definition does it say that complementary angles must be adjacent. So what you could do is come over here and just draw yourself one angle, and I don't know what I drew there, but I'm going to guess that that one is about 30 degrees for the measure of that angle. And then I'm going to draw another one right over here that looks like it's maybe going to be about like that, and I'm going to say that that one is 60 degrees. Now these two angles are not adjacent. They don't have the same vertex, they don't share a common side. But if we look at them pretty clearly, their angle measures of 30 degrees and 60 degrees add up to 90. So these ones are complementary angles here as well. So again, if I called this angle 3 and this angle 4, we could also say here that angle 3 and angle 4 are complementary as well. So they can be adjacent like 1 and 2, but they don't have to be adjacent like 3 and 4. Okay, so that's what the word complementary means when we're talking about angles. The word supplementary means something very, very similar here, but now instead of your angles adding up to a measure of 90 degrees, now they add up to a measure of 180 degrees. So again, the easiest way to draw two supplementary angles is to make them adjacent. A 90-degree angle, which we talked about on the last slide, was a right angle. A 180-degree angle, which we need right here, is a straight angle. So the easiest way to do this is to go ahead and simply draw a line, choose one point kind of in the middle of that line, although there really is no such thing as the middle of a line. It goes on forever, you know that. But let's just draw one more ray now sticking up out of that spot. Now, unlike in the last problem, I had to give you that corner mark there in red to indicate that this angle was a right angle. You cannot just assume from a diagram like this that this angle right here is 90 degrees. That's an assumption we are not allowed to make, that of right angles. But as far as straight angles are concerned, we are allowed to assume from a diagram in geometry that a line that appears to be straight is straight. So we don't need any special markings to understand that the sum of these two angles put together here has to be 180 degrees. So I'm going to go ahead and call this big obtuse angle, or at least it appears obtuse, angle 5, and this smaller one that looks acute, angle 6. And then right here, guys, without any other markings, we can say that angle 5 and angle 6 are supplementary angles. If you know that word from any other settings, the one that I think it pops up the most would be something like vitamin supplements. That if you were not getting enough vitamins from your diet or maybe some type of medical condition, your doctor might prescribe supplements right there, basically vitamin pills that you can take. Supplements are kind of getting you, helping you out and getting you towards a larger goal here, and that's what, I lost my definition there, that's what supplementary angles do. Now, just like complementary angles, these don't have to be adjacent. So you could come right over here, and I tell you what, let's go ahead and draw one angle here and then another angle right over here. And my intent was for those two angles to look like right angles. But of course we can't assume that they are until I go ahead and put corner marks in each of those angles. And now if I call this one angle 7 and this one angle 8, this isn't real tough to figure out. They're both right angles, so their measures are both 90 degrees. 90 plus 90 adds up to 180, so we could now say that angle 7 and angle 8 are supplementary angles as well. Okay, so they can be adjacent like 5 and 6. They don't have to be adjacent like 7 and 8. All right, so that is supplementary angles. The next one, this is one that people struggle with a little bit, so we want to spend some time making sure that we get this definition down. A linear pair, everybody, and remember, pair always means two, are two adjacent angles whose non-common sides are opposite rays. Whew, that's a little bit wordy, and there's a lot of vocab within that definition. So first of all, we're drawing two angles. That's what the word pair means. They have to be adjacent, so they have to have a common vertex, they have to share one ray, and they can't overlap at all. But the non-common sides, the ones that don't overlap, need to be opposite rays. So the simplest way to draw a linear pair is, let's go ahead and through that one point, let's draw one straight line, everybody, that looks like this. And actually, I'm going to go right back to that first diagram that I drew for you on the last slide with supplementary angles. Now, we've got two angles here, and I think I'm at 9 and 10, so let's go with that. So, let's see if this diagram matches the definition right here. A linear pair is two adjacent angles. Well, let's stop right there. Are 9 and 10 adjacent? Do they have the same vertex? Yeah, we'll call that point P right there. So they both have the same vertex. Do they share a common side? Yeah, let's put a point up here and say they both share ray PQ. And furthermore, they don't overlap at all. So yes, 9 and 10 are adjacent angles. Furthermore, the non-common sides need to be opposite rays. Well, let's see. I did P, I did Q. Let's go with R out here, and let's go with S right over here. The side that these two angles share, that they have in common, is ray PQ. Poorly drawn. The sides that they do not share are ray PR, like so, and ray PS. So here's ray PR shooting out to the left, and here's PS shooting out to the right. And because we are allowed to assume a straight line when we see one, we now know that this is a 180-degree straight angle there, and that means that those two rays, PR and PS, we can go ahead and say now are opposite rays. And with that in mind, these two angles form a linear pair. So we would say that angle 9 and angle 10 form a linear pair. Really simple, guys. Pair means two, linear means line. So when you look at this diagram, when you see two angles right next to each other that together make a straight line down here on the bottom, what am I looking for? Here we go. That they make a straight line down there on the bottom, everybody, that's what linear pair means. Two angles that make a line. Now, unlike the last few slides, I can't draw you a second example of this because with both complementary and supplementary angles, they could be adjacent, which they normally are, but they didn't have to be. Well, in this case right here, guys, these two angles absolutely must be adjacent, so I can't draw you a non-adjacent example. They have to be just that. All right, so that was linear pair. Let's move on to number 5. This is one of the most important ones that we're going to see over and over and over again throughout the entire year, but luckily it's not that difficult, even though the name doesn't make a ton of sense. Vertical angles. And our definition of, oh, that's not what I wanted. Our definition of vertical angles is a little bit goofy, but the diagram makes a lot of sense. Two non-adjacent angles formed by two intersecting lines. Now, when I put that up on the board and I say, okay, so do you guys get it? Most people are not going to understand what that means. But we've got to get a pencil in our hand, everybody, and start drawing a diagram so we can see what's happening. Two non-adjacent angles formed by two intersecting lines. Well, the first physical thing that I read in that definition is the two intersecting lines. So I'm going to draw one line, and remember that a line goes on forever, so I'll put arrows there, and another line going this way that intersects the first one. And when two lines intersect, they intersect at a single point. That's one of Euclid's basic postulates of geometry. Now, when we intersect two lines, everybody, we form four angles. I'm going to call them, let's see where I'm at. I just did 9 and 10, so I'm going to call these angles 11 and 12 and 13 and 14. So we've got 4 angles formed by these 2 intersecting lines. And now if I go back and read the definition again, which I just lost, we are looking for 2 non-adjacent angles here. Now remember, adjacent means next to or touching. So if I were to ask you what angle or angles are adjacent to angle 11, just ask yourself which ones are right next to it. And 11 is adjacent with both 12 and with 14. The only angle here that's not adjacent to angle 11 is angle 13. So that, everybody, is a pair of vertical angles. So angle 11 and angle 13 are vertical angles. And if you look at it that way, the name kind of makes a little bit of sense right here. Angle 11 is up top, angle 13 is down here on bottom, and there's kind of like a vertical line that connects the two of them going up and down. What's dumb about that, though, and the reason it doesn't make a ton of sense, there's also a second pair of vertical angles here. If we were to focus starting now on angle 12, the 2 angles adjacent to angle 12 would be 11 and 13. That means that 14 is non-adjacent. So you could also say that angle 12 and angle 14 are vertical angles as well. And now my little trick about drawing the vertical line there to connect 11 and 13 doesn't really make much sense at all. So one of the phrases that one of my students started using years and years and years ago is kitty corner angles. Okay, if you were to think about 2 streets intersecting, these 2 angles would be kitty corner from each other. So 11 and 13 is one pair, 12 and 14 is another. All right, all right. Now, going along with this, everybody, postulate 1.9, there's only a couple postulates in this section, and this is one of them. The linear pair postulate says the following. Now, let's remember, everybody, the definition of the word postulate is a mathematical rule or law that we know is true, but is so basic that it cannot be proven. So the linear pair postulate, as the name would suggest, deals with 2 angles forming a linear pair. And with most of our postulates and our theorems that we're going to get into later on in the year, we like to write them in what is called if-then form. So our linear pair postulate is going to start with an if. So we would say if 2 angles form a linear pair, a linear pair. And now there's a comma that comes after that. And you guys know that when you're reading something, a comma is indicative of a time when you can go ahead now and just take a breath and just, relax and kind of gather your thoughts. Well, that's exactly what we're going to do right now. I'm going to draw 2 angles that form a linear pair. So there's my straight line. There's the point that I start with, and there's another ray shooting off on the side. And if these 2 angles here, boy, I'm up to high numbers right now. I think this is angle 15 and this is going to be angle 16. If those 2 angles form a linear pair, then, and I would simply ask you guys right now, is there anything that you think you know about the relationship between these 2 angles on 15 and 16? And we kind of hinted at this already. We are allowed to assume a straight line here. Actually, it's not even an assumption because it's part of the hypothesis of this if-then that these 2 angles form a linear pair. We know then that those 2 angles added together have to make up a straight line. That has to be a 180-degree angle. That means that angle 15 and 16 have measures that must add up to 180. And that matches a definition that we learned earlier today. Then those angles are, and the word we learned for 2 angles whose measures adds up to 180 is supplementary. And now we know for a fact that the measure of angle 15, in fact, let's write this out, the measure of angle 15 plus the measure of angle 16 has to equal 180 degrees. So it's kind of like using the angle addition postulate, except with a diagram like this, or knowing that they form a linear pair, they didn't have to tell you that the sum of the big angle right here was 180. We can kind of figure that out on our own. So I believe we have an example with that, and this is a pretty common and pretty typical first semester geometry problem, where they give you a diagram that looks like this, all right? And we're supposed to solve for x. Now again, if they had told you, and don't write this down everybody, that the measure of this big angle out here was, I don't know, 18x, minus 11, then we could have done something like the angle addition postulate. Little angle plus little angle is equal to big angle. We already know how to do that, but they didn't give you that information on this problem. They didn't tell us the measure of the big angle, but we now get to figure this out on our own. And the only way this works is because there is an assumption that we are allowed to make from this diagram, and that is that this line down on the bottom, and let me go ahead and call that A, and that B, and that C. So line AC down here on the bottom, basically we are allowed to assume that it is in fact a line. And a straight line at that. There's no such thing as a curved line. So that means that we know for a fact that the sum of those two angles right there is 180. We can assume a linear pair from a diagram. That's the important thing, and let me say that a second time. We are allowed to assume a straight line, therefore we are allowed to assume a linear pair from a diagram. So if I was going to talk about angle ABD, which is this angle right here, and angle DBC, which is this angle here, we now know that those two angles form a linear pair. And the postulate we just learned said that if two angles form a linear pair, then those angles are supplementary. So that means that these two angles are supplementary, and we can now apply our understanding of supplementary angles to solve for x. The definition of supplementary angles are two angles whose measures add up to 180 degrees. So the measure of the first little angle here is 3x plus 1. We would add to that the measure of angle DBC, the other angle, which is 9x minus 13, and because they form a linear pair, that makes them supplementary, and that means that they add up to 180 degrees. So now it's a pretty easy equation to solve. The 3x and the 9x makes a 12x. The plus 1 and minus 13 makes a minus 12, so that equals 180. I'm going to add 12 on both sides here, everybody, and I think you guys will be okay if I don't show that. Adding 12 to 180 is going to get me 192, and then we're going to divide both sides by 12. Probably didn't need to show this either, and we're going to end up with x is equal to 16. Now, the directions to the problem were simply to solve for x, so I believe that we're done. But it is always a good idea in geometry to take the extra moment and make sure you've got this right. Here's how we can test it. If x is 16, let's plug that in right here. 3 times 16 is 48, plus 1 is 49 degrees. That doesn't tell me anything, but now let's keep going. 9 times 16 right here is 144, and 144 minus 13 is 131 degrees. And if I think about 49 and 131, if we were to add those two together, yep, that makes 180 degrees, so I feel really confident that that answer is correct. Okay, so that's how we handle a problem like that. One thing I want to stress before we move on, though, is that you guys really take the time to memorize that you take the time to memorize this definition very, very carefully. Our definition of supplementary angles is two angles whose measures add up to 180 degrees. I bring this up because year in and year out, people omit those three words, and they simply equate in their head that supplementary means 180. And let me show you the mistake that people make then all the time if they just think that supplementary means 180. they'll get to a problem like this and they'll say, okay, those two angles are supplementary, which means they're both 180. So they'll do this. 3x plus 1 equals 180, and they'll solve that. Then they go 9x minus 13 equals 180, and they solve that. And they end up with two different values for x, both of which are wrong. You've got to commit to memory, everybody, that supplementary doesn't mean 180. Supplementary means adds up to 180. So there's no such thing as one supplementary angle. You need two supplementary angles whose measures add to 180 degrees. All right, so that's really important to make sure that we understand. Supplementary doesn't mean 180, it means two angles that add up to 180, and we need to make sure that we have that down. Last vocabulary term of this section, everybody, is angle bisector. And if we thought about this word bisector, we've defined it earlier in the year with a segment. Now we're doing the same thing with an angle, everybody. And the word bisect, let's break it down. The prefix bi means two, and the sect, S-E-C-T right there, is a portion of something or a part of a whole. To dissect something, like you might dissect a frog in biology, means to cut it up into pieces. Bisect specifically means to cut it up into two pieces, not multiple, but two pieces that are the same. So a bisector cuts something in half, all right? So our definition for an angle bisector is going to be a ray, what do I want to say right here? That divides an angle into two smaller congruent angles. And that's an important word, everybody, congruent. And if you don't have that word pretty well committed to vocabulary already, we better get it down. Congruent basically means geometrically equal or having equal measures. All right? So if we wanted to draw an angle bisector, I'm going to start off with a big angle. I'm going to put a point here and one ray shooting out to the right and another ray shooting up this way. And I'm going to call this point X. This point right here is going to be Z, and this point right here in the middle we're going to call, we'll call J. So we've got one big angle here, that would be angle XJZ. So here's our angle, and we want to draw the angle bisector of this angle. So it's going to be a ray. I didn't write this down, but this ray needs to come out of the same endpoint as ray JX and JZ. So another ray, everybody, that comes out of point J and basically bisects or cuts this big angle in half. Cuts it into two smaller congruent angles. So I'm just eyeballing this here, guys, but it is going to look roughly something like that. And I'm going to call this point Y. So the ray that I just drew is ray JY. And I don't know that I got it quite right, everybody, but my hope would be that the two new smaller angles would be congruent to each other. Well, we are not allowed to assume from a diagram, even if I did do a good job of drawing this properly, we are not allowed to assume that angles are congruent. So I'm going to have to use tick marks here, guys, and I'm going to do a double tick mark here on top and then a double tick mark here on bottom. So now we know for a fact from the diagram that angle XJY, this angle right here, and angle YJZ, this angle, are congruent. And since those two angles are congruent, we can now conclude, everybody, that ray JY bisects angle, and the big outer angle was XJZ. Okay, ray JY bisects angle XJZ because it comes out of the same endpoint, the same vertex, and it created two smaller congruent angles. All right, so with that in mind, one more example and then we're done for the day here, everybody. So we're going to solve for x in this figure. So what do we see? The first question you guys might want to start asking yourself, and I think you've done this already with the angle addition postulate, how many angles do we have in this figure? The answer to that is 3. Some of you probably said 2. You probably looked at this one on top that's labeled 6x minus 4 degrees and the one on bottom that's labeled 3x plus 11. But of course there is also another angle here, the larger outer angle, which would be this one right here. So there's actually 3 angles presented to you in this problem. And if they gave you the measure of the big yellow angle, we could do the angle addition postulate. Little angle plus little angle is equal to the big angle. However, they didn't do that, but they did give you something else that's really important, and that's the red tick marks. The red tick marks tell us that these 2 angles, the small angles, are congruent, and that this ray right here in the middle is an angle bisector of the larger angle within this figure. So they didn't have to write out the words angle bisector. The tick marks here and here tell you that same story. And because those 2 angles are congruent, it means that their measures are equal. So 6x minus 4 must be equal to 3x plus 11 because the tick marks tell us that those angles are the same. So what are we going to do here, everybody? We're going to subtract a 3x from both sides and bring all the variables to the left. At the same time, I want all the constants to move right, so I'm also going to add a 4 on both sides as well. 4's on the left cancel, 3x's on the right cancel. 6x minus 3x is 3x. 11 plus 4 on the right is 15. We divide by 3 and we get x is equal to 5. Now again, the directions said solve for x, which we've done, but it's always a good idea to check your answer by plugging it back in. So if x is 5, 3 times 5 is 15. 15 plus 11 gives us 26 degrees for the measure of this angle. That by itself doesn't tell us anything until we also try it here. 6 times 5 is going to get us 30, and 30 minus 4 is also 26 degrees. Those 2 angles were supposed to be congruent because of the double tick marks that they both had, and it looks like they are. So that doesn't guarantee that we got the problem right, but it makes it very, very likely. And of course, if we were asked now to come up with the measure of the big yellow angle, we would take the 26 and the 26 and add those 2 together to get 52 degrees for that angle right there. Okay, everybody, that is a wrap on section 1.5. Hopefully it's not too bad. Let's give that homework a shot and see how we do on that. Good luck, and let me know if you guys have any questions by posting in the comments on Google Classroom.